Okay, I think we're recording.
All right, so today I really want to do a lot of concrete examples. And by that I mean, we mean concrete examples of modular curves. So roughly speaking, um, you could measure my success today by how many modular curves I draw on the whiteboard. Uh, and every time that I draw one of these modular curves on the whiteboard,
Let out a cheer.
no. Every time I draw one, there's at least two things that I'll probably be drawing accompanying it, kind of next to it. One thing is what I call this, sometimes call this split screen picture. So, you know, the modular curve is supposed to be interpreted as a moduli stack. And so I'm drawing the moduli stack, and then on the other side of the split screen, I'll be drawing some sort of depiction of, you know, how you should think about a particular point of the moduli stack. And I may point with a cursor or something like that to a particular point of the moduli stack, and then I'm supposed to, you know, have the picture ready for that particular point of the moduli stack. So that's one of the things that we should be drawn next to, in split screen style, next to the modular curve as a moduli stack. And then underneath those pictures, I may sometimes, sometimes at least, if I know how to do it, I may write a sequence of numbers, which is supposed to be a sequence of like dimensions of spaces of modular forms or something like that. And so you can already tell that it's a sequence of numbers, that it's getting into a way of understanding these modular curves that's in some sense more than just visual. Although it'd be nice if we could really get it so you can just read the numbers off from the picture in some very straightforward way. I'm not sure I'm ready to do that yet, but it'd be nice if we can do that. And so yeah, so that's what I really want to do. You know, if I don't do that, then I'm screwing up. But even though that's what I really want to do, I just want to start with a very brief discussion of, or recap of, some overall strategy. I'm really trying to not let this distract us from getting to the concrete examples. But let me see if I can just say a little bit, reminding us, especially reminding me, of some of the overall strategy here. So while I'm still learning how to use this tablet here, all right. Sort of know how to use a tablet. I'm still learning how to do the tablet software. So so ostensibly, I'm trying to learn from these notes written by Nigel Boston in 2003. One of the key goals of the part of the notes that I'm really trying to understand, that I'm really trying to learn from at the moment, is this goal of extract nice Galois representations extract a nice Galois representation from a nice modular form. That's a very oversimplified description of one of these goals that's discussed in these notes, especially in chapter 4 in the section on modular forms, especially theorem 4.28. So I talked a little bit about this last time. And and I just want to make a very brief attempt to maybe repair some of the things I said about this, to maybe try to make them sound more sense in terms of how this is going to act as a guide to our overall strategy in learning stuff here. So well, I think what I said was something like this, or I may even have drawn this or written it on the whiteboard, something like that you have a modular form. And there is something that you could do with this modular form, which is that you could get a modular representation from it. Sorry, we're trying to learn here. A modular representation here. And perhaps in this context, you should sort of take that word modular and generalize it in your mind to automorphic, because all this modular stuff is supposed to be a very key, even introductory example of automorphic forms and automorphic representations. There's this thing that you could do to a modular form to get a modular representation. And the way Nigel Boston seems to operate in these notes is that they seem to almost do this, except at the last minute they sort of veer over and instead they get a Galois representation. And the way they do that, well, this is the part I don't want to get bogged down, but it has something to do with the idea that if you're getting the modular representation, then you would be working with like functions on the modular curve or something like that. But instead, to get the Galois representation, you start thinking about the Jacobian variety, the Jacobian abelian variety of the Galois representation. And
I'll just mention to Chris that that's an abelian variety is like a higher dimensional version of a elliptic curve. I mean, an elliptic curve is a one-dimensional abelian variety.
Yeah.
So some of the stuff I was telling you about getting
more over an abelian group, right?
I couldn't quite hear, but I think you're right. Can you say it again, Chris?
I said an abelian variety is a variety that's more over an abelian group, I think.
Yeah, perhaps then compact projective or something like that.
Oh, okay, sure.
Or projective maybe implies compact. I don't know, whatever.
I don't know, but yeah.
Yeah, so this stuff
certainly in the ballpark for a definition of abelian variety. Sorry, go ahead.
So this stuff telling you, Chris, about getting Galois representations from elliptic curves is probably a baby case of getting them from abelian varieties.
That makes sense.
That's true. That's true. I mean, again, I said that, you know, in our minds we should be generalizing modular to automorphic here, and I'm going to just do that on the whiteboard here, even though it's probably too ambitious at the moment. But I just want to have the words here on the whiteboard. Not automorphism, automorphic. Let me try to erase that. I don't want to think too much about how automorphic is related to automorphism, so I'll just try to write here, automorphic. Okay, so this is very roughly what Boston's strategy is in these notes, but so much so that you could probably perhaps reinterpret this diagram slightly, that what you're really doing is you're actually going this way. You're actually going from the automorphic representation to the Galois representation. Now, I'm not saying that at least not in this part of the notes, I'm not saying that Boston is actually doing it this way. I'm just saying that he's hinting it this way. So when I try to really learn concretely from what Boston is telling me, I'm not going to be thinking, I don't think, unless they start switching around, I'm not going to be thinking of it from the point of view of turning an automorphic representation into a Galois representation. But maybe I should. I mean, I'm saying that, I'm saying that Boston is just hinting at this. But it's a very promising hint because it sounds like slogans that we've heard in connection with the Langlands program. So the Langlands program does seem to be talking about stuff that says that perhaps from an automorphic representation or perhaps associated to an automorphic representation, there may also be a Galois representation. And the Langlands program may say that every Galois representation optimistically comes from or is associated to or associated from an automorphic representation. So I'm just saying that what Boston is doing in these notes is promising to me in terms of making me optimistic that I might be learning about the Langlands program. And of course, maybe in the later part of the notes, they may say this more explicitly, but at this point, I'm just trying to read the hints. And again, just to try to remind myself of the overall strategy here, what we're about to jump into with the concrete examples here is all directed towards getting examples that we can, getting examples to which we can apply Boston's description. So, Boston's process, Boston's description of this process for getting the nice Galois representation from the nice modular form. So in other words, all my concrete examples are more or less directed at getting these examples of nice modular forms. So that's my overall strategy. And now I'm going to try to really get into the concrete examples. So let me try this now. So let's move the whiteboard down a little bit. So the way, right. So again, this is, as usual, this is multi-brow thinking. We're going to do some very low-brow stuff, very high-brow stuff. Except I can never tell which is which. I can never remember which is the lowbrow stuff and which is the highbrow stuff. But I have a feeling that the lowbrow stuff includes these drawing pictures of Coxeter groups and stuff like that. Let me semi-remind us, really just by jumping into examples of what a Coxeter group is. So it comes from a Coxeter diagram, and the particular example that I'm really interested in at the moment is this particular Coxeter diagram. Now, I have to try to remember where the numerical labels are here. I think opposite, if I think of this as a triangle, the third leg of the triangle is somewhat invisible, the leg from green to red, but that's okay. Invisible sides of a triangle in this Coxeter diagram game signal that there is an edge there, but it's invisible, which means that the label is 2. It's sort of so generic or something that it's you don't even have to draw it in. But then but the ones that are labeled with a 3, you don't have to put the explicit label 3 either, but you make it visible. But you make the label invisible. So there's an invisible 3 right there. And, there's an invisible 2 right there. Let me erase the invisible stuff.
I'm not erasing now. I mean, Chris is just learning this stuff, perhaps. So it's not.
I've seen some.
I think it is good to erase the invisible stuff because that's what you'll see in the book.
Okay.
So I'm erasing the invisible 2, erasing the invisible edge that has the 2 on it, erasing the invisible 3, but trying to erase the invisible 3, but not erasing the edge that had the 3 on it, because that's the convention. But okay, but the one over here, okay, I think I said that there are numerical labels on here, but I don't know how much you like regarding that as a numerical label. But you know, it's a sort of number, infinity. So the dots in the diagram, and I like making the dots different colors. I don't see too many people doing that regularly, but I don't mind. You know, presumably for colorblind people, you need some sort of system to substitute for the colors, but that's easy enough to do. So the dots represent generators. By the way, one of the interesting things about this game is that you draw these sort of hieroglyphic diagrams, and then it turns out you can read the hieroglyphics in multiple ways. So like I'm just sort of describing only one of the many things that you can do to extract something from a Coxeter diagram. And the thing I'm talking about is, I guess, called a Coxeter group. So the way you get a Coxeter group from the Coxeter diagram is you interpret the dots as generators of order 2. So I guess we call them involutions or something like that. And then you interpret the numerical labels on the edges as relators between the generators. And so they basically tell you the order of the composite of those 2 generators. And I guess that makes sense as an undirected edge. Yeah, it's the order is the same regardless of which way you multiply the 2 involutions, right? Because that would just be the inverse thing, and the inverses have the same order. Yeah. So yeah, it's generators and relators, so it could give you an infinite group. This one does give us an infinite group. Let's have one example to give us a finite one that we can draw. So let me draw a different Coxeter diagram. How about sorry. Do you have a favorite one, John, for numerical labels?
Like 3 and 4.
3 and 4. Okay, so the 3 is invisible. Try to erase that 3 in your mind. Yeah. And so yeah, let's try to draw this whole thing. So right. So there's a you know. So what is this thing that I'm about to draw called? I guess it's called the Coxeter complex, and it's a depiction of the Coxeter group. So let me try to do the one down here. So it's like, okay, don't tell me, let's think about how this works. So let's see, you know, in this case, I have 3 dot diagrams, which means they're going to give me sort of planar pictures. And I guess that's why I chose 3 dots, because it's easier to draw planar pictures than spatial pictures or something like that. So, so what have we got here? Don't tell me. Let me think about it for a second. Unless you're dying to tell me. So, okay, the Coxeter complex, it's sort of simplicial complex. Maybe I just start trying to draw, get my hands to do the thinking instead of try to think about it. Let's see. So, don't tell me. Let me think. Okay, I guess what's going to happen is that because there's 3 dots, that means that the fundamental regions. So yeah, I'm going to draw the group. We're going to depict the group by having it act on something. And it's going to act on something like a plane. something like a 2 manifold. And the fundamental regions for this action are going, is that good? Fundamental regions, fundamental domains, whatever. They're going to be, roughly speaking, triangles. And they're going to be triangles with one vertex of each color. And so let me try to do that. So, yeah. Okay, that doesn't look the right color. Sorry. And sorry, still trying to, okay. Green, okay. So I've got a green and a blue and a red. And now when I'm drawing this picture of the action, I'm not trying to make the edges invisible. Boy, I accidentally used a reasonable color coding there, but for now I'll just make all the edges black. It would be interesting to make, it would be an interesting convention to make the edges the same color as the sort of complementary vertexes. But that seems like too much work at the moment, so I'll just make the edges all black. So that means including the invisible edges, for example, are black. So how does this work? I erase the, okay, and I put things in black. Okay, and I'm going to mark this one with an asterisk, meaning it's special, it's favored, it's the base point. It's yeah, it represents the identity element of the group. And then you just start putting in reflections of, you know, because the involutions are going to act in a sort of reflection-ish way, right? Because involutions are like reflections. So there's going to be, you know, another blue thing. Sorry, that didn't look very blue. See, I'm not, I don't have this facility with switching back and forth between.
Yeah, you were so quick at it with the other system.
Well, was I trying to do the same thing? I don't know.
Well, maybe I wasn't so focused on how fast you can do it.
There's something, yeah, there's something about I have to go way over to the one side. I don't know.
It looks especially funny on this view that everyone sees because you're going to some region that doesn't seem to have any special properties and you're drawing from it the ability to write in color. But yeah. Okay. So he reflected the triangle in such a way that the blue changed. The blue dot vertex turned to a new one. So that was the blue reflection.
And yes, and because of the nature of reflecting across a hyperplane or whatever it's called, it switched orientation. So in fact, the fundamental regions here are going to be alternating orientations. And we could, you know, like Moritz Escher or something like that, has pictures a lot like this, where like the alternating orientations are maybe black and white or something like that. And that gives, you know,
angels and devils,
something like that. Or what are some of the other ones? I don't know, frogs.
There's ones with the lizards.
Lizards and other lizards, black lizards and white lizards.
Black and white lizards, yeah.
Okay.
He was talking to Coxeter. He was friends with Coxeter.
Right. I guess, right. That's, yeah. But I guess part of the point is that the angels, right, the part of the cleverness of the craftsmanship is that you actually have, because it's reflections, it's involutions, it's symmetries, you have to make mirror symmetries. You have to make the angels look like the devils, except for some very slight difference that, you know, makes the angels black and the devils white or something like that. But of course, Escher did it in some very craftsman-like way. So, right, maybe while I've got the color set on black, maybe I can draw a bunch of edges. So there's this thing like that. Is this going to work?
This doesn't have any fourishness to it.
Yeah.
If you,
but that didn't bother me yet, did it?
Well, no, not yet. No, not yet.
So, right, around a green, there should be 8 of these triangles because of the 4 on the label opposite the green. So it looks like I got, yeah, I better fit 5 of them in here, right?
Oh, no.
Am I doing this right?
Topologically.
Well, I mean, right? I mean, we did hint that this is going to give us a finite example, which might suggest that it's going to be like spherical rather than like hyperbolic or flat or something like that. So, you know, we're drawing something that's really round, really spherical. We're drawing it on flat paper. So it shouldn't bother us too much if we're, you know, topologically distorting the angles. Am I screwing up here, John? Do you want to jump in and draw? Can you jump in and draw stuff, John?
Well, never mind. It's just been anyway. Go ahead. No, you're not screwing up. Not according to your self-established rules.
Okay, so let's see. So how do I fit? I'm just totally capable of fitting 5 things in here. It's like that.
Yep, something like that. Is that a total of 8 of those guys? 1, 2, 3. Yeah, right. Yeah.
But
so the idea there, Chris, although you seem to have gotten it, is that if we take that starred triangle and we switch its red vertex,
right,
then we're hopping over to the triangle, to the triangle near the top. And then if we switch the blue vertex of that one, we're hopping over. So if we keep going red, blue.
And we know red, blue to the 4.
Yeah. That by the time we do red, blue 4 times, we got to get back.
Yes, so there's this very dihedral thing going on here where the composite of 2 involutions is a rotation. And you can see that in the picture. The composite of the 2 reflections, reflecting the blue dot across the thing and then reflecting the red dot across the opposite edge. So the point is that these edges in the dots, what I'm struggling to say is that the dots in the Coxeter diagram correspond to reflection operations, whereas the edges in the Coxeter diagram correspond to these rotation transformations. So for example, there's the composite of the blue and red, and so that is rotating around the green dot. Now, again, right, I mean, so this is a 2-dimensional example, and then there are all sorts of special things about 2 dimensions that make it very nice, but also make it so nice that you get used to it and you start thinking, oh, I'm going to have this when it get into higher dimensions too, but you're not going to have it in higher. So, for example, if you had 17 dots, then you use 2 of them, any 2 of the dots, give you a rotation by composing the reflections. But what is that a rotation around? Well, it's a rotation around the codimension 2 simplex given by all the remaining colors. So there would be 15 remaining colors. That would give you am I saying that right? Codimension 2 simplex. And this rotation would be a rotation around that simplex. So in higher dimension, you have to visualize a rotation where the axis is a higher dimensional thing. I mean, already in 3 dimensions, we're very used to the idea that a rotation is around a higher dimensional axis. It's not just around a point. But in 2 dimensions, a rotation is what's that?
Dimensions I can visualize much easier than 16 dimensions or whatever 17 minus 1 should be. And the codimension 2 thing is then just a line. And
yes. And and we're very familiar with the idea of a line as serving as an axis for 3-dimensional rotation. That's right. So these dot colors going around the green are going to alternate blue and red. So let me try and see if I can get that to work. So they're going to be blue.
I'm going to meanwhile pose a puzzle for them all over, which is that if we continue doing this, pick it right, that is, just to follow the rule, what picture would we finally get? That is, what sort of thing would we?
And it's all going to be up to topological equivalent.
Yeah, we'd be getting a 2-dimensional thing that was subdivided into a lot of triangles. And so, but the question is, like, what would it look like? So far, we're drawing it in the plane, but as you can already begin to see that that's going to get sort of ugly.
Yeah.
And so it turns out you get something quite nice if you.
Can I just say a few things about, so like, around the green, we had 8 triangles because of the 4 label here, but the invisible 3 label on the edge opposite the red thing means that going around the red, we're going to have 6 triangles. So that fits nicely without squeezing too much. Going around the blue, opposite to the blue is the invisible edge with the
We should
label
expect a
2. So
square.
there's just a thing like that. Are you hinting at, did you suggest something, Chris, about what the whole
Yeah,
thing?
I said you should expect a square around the
Yeah,
blue.
but you're already giving a big hint about the answer. That like, what if you just visualized the red dots as like corners of something? The red vertexes.
Sorry, where did you say it was a square, Chris? I'm sure you're right.
Yeah, going around the blue dot, you should have a square of red, green, because red and green commute. Right?
You're probably right. Yeah, you're right.
Yeah, a green. Yes. Sorry. So you're just telling me to put in a green over.
Yeah. So a green should go there.
Go there.
Maybe my lack of knowledge of various tessellations of platonic solids means that I don't.
Yes.
I'm not seeing what I should be seeing here.
Well, I think I asked for what the red would be like as corners.
But Chris seemed to be saying that each blue dot would be the center of a square. Is that what you're?
Yeah.
Right, but I think I sort of made a mistake. I think I was suggesting that the blue thing might be corresponding to a square side, but I think that's actually
a square side, a square face. I mean, Chris was saying each blue dot is in the middle of a.
I meant a square face or something like that. But I think it's actually the green things that are corresponding to square faces.
Uh-oh.
I think right if you sort of rearrange things so that so that these things really look like square. Sorry, that's supposed to be black. Black.
Well, how come you had us in the picture? So you're saying the picture above is wrong?
I'm saying topologically it's correct, but I'm saying if we can draw it in a more suggestive way by taking advantage of the topological freedom.
When you say that the green corresponds to a square, you mean you're going to treat this octagon as a subdivided square.
Yeah, that's okay.
Okay.
Now I get why you said what you said, Chris.
Yes,
and why
that's right. That's right.
Okay.
So yeah, they're going to be red corners of the square here, I think. And
I'm happy.
I'm sort of taking guesses about the best way to do it, but guesses based on vague memories. That was the wrong color.
At least this is nice, Chris, because when you draw it the way that Jim is now,
I really need my
the reflections of these little triangles that he's eventually going to draw, they preserve the shape of the triangle. So we're doing not just topology, but geometry so far. So which is what we're aiming for. So that little portion that Jim is drawing now is sort of working out.
I'm really bad at this. I really need an undo button.
Okay. I can I don't want to sort of do what you did.
If you can read my mind and tell me what I want, I don't want everything. You might think I just want to undo everything I do, but that's not quite true.
Yeah.
So what am I trying to say?
Okay, so go on and continue to try to guess, Chris, based on the new.
Yeah. Okay. So let's see. It would be really nice if I could say for sure that there were going to be 6 greens total. The obvious guess would be a cube.
Yeah, that is how it's going to work out. I mean, you could sort of see. Let's try that and see if it works.
Okay, so Jim just said yes, it's a cube. Okay, so so if you start drawing this cube, you see that each red has 6
I mean, Chris did.
Does, and each blue, okay, I see it, I see it.
Yeah, let me try to.
So yeah, so you don't really need to work out the whole everything. You just sort of need to work out enough.
Yeah, yeah, I
Well,
see.
I don't know. If you want to check a guess, there's enough now to see that like it's gonna have to be a cube.
Yeah.
Or at
I
least
I thought they did state the guess, and we're just kind of.
Yeah. I'm trying to figure out if there was a
Yeah.
quick way that I could tell that there were.
Chris stated it, but in a very tentative way, and you said, "Yep, yep."
That's what you're supposed to do. That's
Okay, you
you're supposed to
deprive
encourage
the,
people when they
the
get the
whole
right answer.
thing of its old drama. Like if you're like on a quiz show and you win by guessing the answer, they go, "Yep."
Yeah, I guess we should have really cut to a commercial there.
Yeah, right, that's right. Okay.
So
When
So
you
what
get
do you
the
have-
answer right, I that means I instantly know that, aha, they now understand the whole thing.
Yeah,
yes,
right.
I'm happy now.
So what we have done, Chris, which is really cool, is we've described actually, well, it's not obvious from what we said, but we've described the symmetry group of the cube.
Yeah.
In terms of these generating reflections, where we're reflecting around, well, and the relationships that they obey.
Yeah.
So this is like a famous group. And this, well, I just happen to know it has 48 elements for some reason, but there's tons of good stuff to say about it. It has.
Is there a bonus reflection there? Because isn't the symmetry group of a cube S4, which I guess has 24 elements probably?
That's the rotations, is that right?
Is that just the rotations?
Yeah, that's just
Yeah,
the
there are
rotation.
4 long axes of a cube, and you can freely.
And you can permute them. Ah,
and I'm going by vague memories here.
flips
Don't
through the
trust me
base?
on these details.
Is that where the bonus
Sorry?
factor
Yeah.
two comes in?
The even permutations of the 4 long axes of a cube turn out to come from rotations of the cube. Like if I hold a cube at diagonally opposite corners, then there are 3 other axes, and as I turn the cube around, I'm cyclically permuting the other 3, and so that kind of thing is an even permutation.
Did I miss here or screw up or something? Is there any way you could just repeat what you said without my having to go back and listen to the tape?
I was saying that if you hold a cube by its opposite corners along one of the long diagonals,
yes, then
as you rotate the cube around, you can accomplish any cyclic permutation of the other 3 axes. So you're getting a A3 sitting inside this larger group of all symmetries of the cube. But since that one axis was arbitrary, we're going to be able to get any even permutation. And so that'll give us A4 as the rotational symmetry group of the cube.
Am I screwed up? I thought we were going to get S4 as the.
No, I was talking about the rotational symmetry group of the cube. But we're gonna get we're gonna get more because we've got these reflections coming in. So if you allow yourself,
I'm still confused. I'm still confused. Am I screwing up here? So okay, 3.
Oh, I'm probably mixed up. No, I probably said something stupid too. But I think
I think you just said it wrong or something like that.
Well, without thinking about the diagonals, you can orbit stabilizer this, right? So first take whatever of the faces you want and put it on top. And there's 6 ways to do that because there's 6 faces. And then you can act on the square however you want. And there's 8 ways to do that because that's the dihedral group of a square. And among other things, 8 times 6 is 48.
Yeah. So you're right. So you can count the number pretty quickly like that. And yeah, no, I was completely screwed up about like what group you were getting. So it's not. Yeah.
Maybe mine doesn't tell you so much about the structure, but it at least tells you.
But we don't even need
the key point is that you already mentioned that if you count these things, there's 48 of them. I mean, we only see 24 because we're only looking at one side of it. But on the reverse of the picture, there's another 24. And that's
so what's so cool about this?
That's twice as many as 4-bet.
Yeah. So what's so cool about this picture that Jim is drawing, Chris, is that the symmetries of the group act in a free and transitive way on those little triangles so that you can, and And so what it means it's so cool is that the set of these 48 triangles is what you call a torsor for the symmetry group of the cube. So if you pick any one of those little triangles to be your favorite one and say that's the identity element, then there's a unique group element mapping it to any other one. And so then you're actually then you can identify the set of triangles with the group itself, which I think is so that was like really blew my mind when I heard it, because it meant that like you can draw the symmetry group of a cube on a cube.
Yeah.
As these triangles, but only if you pick an identity element. So you're really drawing a torsor.
So yeah, so this is just, you know, a good example to learn about Coxeter groups. In particular, the fact that it's finite means that you can, you know, exhaustively check a lot of stuff. But we're also really interested in this infinite example, which, because of the infinity, it's maybe not surprising that you get something more hyperbolic instead of spherical. Let me try to scroll down a little bit. I still get confused about scrolling down versus scrolling up. So
before we do the infinite example, do we want to take a second to talk about what this has to do with these automorphic forms? Like so I agree this is a cool example and I love Coxeter groups, but where exactly are we headed with this?
We are, modular curves are going to be, well, okay. At first I didn't have an answer to your question, but now I think I have an answer to your question. So let's look at the cube one, okay? Let's look at the cube one. But now, so we got this 48 element group. And one of the things we want to do is we want to think about arbitrary subgroups of this 48 element group. And we're going to think about various things that you can do whenever you have a subgroup of a Coxeter group. And one of the things that you can do when you have a subgroup of a Coxeter group is you can use the subgroup as instructions for how to wrap up the this universal Coxeter tiling into a non-universal Coxeter tile. So it's going to be like this universal thing is going to be like a branched cover, you know, a ramified cover. So that, you know, I guess before we turned on the tape, somebody was talking about ramification, but it's actually connected to what we're talking about today. So, right, you can sort of tell where the ramification or the branch points are going to be. It's going to be at the vertexes or something. Well, you can sort of guess that, but when we actually say how to do it, then you can see it. So let's try to do this by example. Let's try to think of some interesting subgroup of this 48 element.
Are you answering Chris's question about what all this has to do with modular forms?
Yes. Yes.
Yes. Okay. Well, I knew you thought so.
Because I'm saying that the universal Coxeter tiling is not the only important thing. It's not even the most important thing. The more important things are these ways of wrapping up the universal one into a non-universal one that are associated with subgroups. And we're going to apply that to this infinite one. And we're going to wrap
Let me just say, okay, I'm gonna just give some stuff away. So the modular group, whatever it is, SL2Z or PSL2Z, you can think of that as a group, as one of those anyway. I guess SL2Z you can think of as a Coxeter group.
Can we start
but it's
drawing
infinite.
That? Can we start drawing that?
Sorry?
As you're talking, can I start drawing that?
Sure, yeah. And so, but that's infinite. So it's going to be one of the more infinite versions of these. But then what Jim is now also saying is that if you pick a sub of that, then you play this game, you'll get well, when you do it for SL2Z, you must get some sort of infinite sized thing, some like infinitely extended surface. And it's probably going to be like the upper half plane or something like that. And then if you take a subgroup of it, you're going to get some
Can somebody undo my
other,
black?
you're gonna get some other thing that's has this as a branch covering of that. And so this other smaller curve that's covered by the branched by the upper half plane, that'll be a modular curve. That's what a modular curve basically is by definition. It's
I'll have to put the lines back in.
Line back.
Okay.
Right. Thank you.
So all these
Yeah.
the integers on the boundary axis of the upper half plane are going to be green dots, and these are called cusps. And there's one more that's well, okay, all right. It's not just the integers. There's going to be more between the integers as well. It's going to be like at all the rational numbers, I think, or something like that. And then in addition to the ones at the rational numbers, there's one more towards infinity.
Mm-hmm.
That's actually
okay.
And let's see. So doing this right. Right. This is getting us back to a moduli stack of acute triangles that we drew at one point.
Mm-hmm.
So let's see. So this is like 0 and 1 and 2 and 3. Sorry. 2 and 3 and -1 and -2 and -3.
As you're drawing this, is the idea here that I guess subgroups of SL2Z act on the upper half plane, and so you can take a quotient, basically treat this as like deck transformations. You get something that looks like a Riemann surface.
Yes, that's like I say that we're taking the orbit space with respect to this subgroup, and so that if you took the orbit space with respect to the whole Coxeter group, it would just give you a single triangle. I guess actually would give you a pair of triangles, an angel triangle and a devil triangle. And that would be like the Eastern Hemisphere and the Western Hemisphere of the Riemann sphere. And it would have 3 green dots on the prime meridian.
Mm-hmm. Right.
I'm still trying to draw more stuff here. Trying to figure out where all the colors are. So far, I only have some of the green stuff. By the way, the fact that there's sort of like translation symmetry here is related to the idea that there's an infinite label. If you know, back up where our Coxeter diagram.
Yeah, unfortunately, we have different opinions about where that picture is, but we do.
Okay.
But on the screen, big screen, the audience sees that infinity there. So
yeah.
Okay. And you know, let me see if I can get some of this to work. So, you know, if you're trying to remember how this all works, just like this and this. So this is really supposed to be I right here, the imaginary unit I. So it's supposed to be the same distance from 0 as 1 and -1 are. I'm not sure how well I drew it in there.
the one frustrating thing about the way you're drawing this is with the cube, we actually sort of started from scratch, just trying to figure it out.
Sure.
And then at the end, we said, "Oh, it's a cube." Whereas here, you're just sort of like serving it to us on a silver platter, which may be a good idea, but
well,
it's hard to see where it's all coming from. It has to come just from
no, but there's a good answer to that. There's a good response to that, which is that, you know, we can give explicit conformal reflection operations on the upper half plane that correspond to the 3 colors, and I'm guessing that the blue one, for example, I'm guessing that it would be like something like sorry, I was going to write a matrix, but maybe I'll write it in sort of the other form where it's like, don't tell me what it's called. It's called the Möbius transformation or something like that. It's like Z goes to, is this in blue? Okay, this is supposed to be the blue one. Z goes to -1 over Z. Maybe that's right.
That
And
sounds good. So that's like conformal inversion followed by negation so that it maps the upper half plane to it.
yeah, I mean, right. So in other words, we could just write down these involutions and then we can draw the picture of that and check if it's satisfying the Coxeter relations. And so the red one is going to be Z. I think it's 1 over 1 minus Z. And I think the green one is going to be Z plus 1. So, you know,
Not
so
an involution. That last one's not an involution.
I'm sorry. Okay. And I think none of these are involution. Well, except
Yeah, no, first
well, but I sort of screwed up.
two actually, I think they are.
No,
The
I
first
I screwed up by drawing the I drew the rotations instead of the
Oh.
reflections.
Okay.
But it's the problem is that the reflections are not holomorphic. So I can't just write them as holomorphic functions. I can't just write them as
Oh,
polynomials.
right. Yikes. Yeah, sorry. So they'd have to have some bars, Z bars, and yeah.
Yeah, so I guess I'm really cheating here, and then I'm giving you the formulas for the rotations around the 3 colors here, I think. So
Okay, fine.
you know,
But
so
anyway, this is even more Deus ex machina than the previous approach. So anyway, but I'm not saying we should do it, but there would be an approach where you just like took a triangle and we started
sure.
reflecting it. And it would be weird because one of those infinities would mean that we'd have to like draw a triangle that had like a really infinitely skinny corner so we could reflect around it infinitely many times before it got back. And we'd work and work and work, and then eventually we'd start realizing, oh, it'd be better to draw it so that it looked like what Jim is doing here.
Yeah.
Well, we are going to draw alternative pictures of this that look a little bit more like what John is suggesting. But let me point out a couple of things about these things that I wrote down here. You can see, did I say this correctly? Z goes to -1 over Z. I'm hoping that that's order 2.
Yes, that's why I was thinking that, yes, you were drawing the reflections, but that was a
right.
coincidence.
But Z goes to 1 over 1 minus Z. You know, that permutes infinity, 0, and 1. So it's like order 3.
Oh yeah, this is this famous thing. It's a famously weird fact, Chris, that if you do that function to itself compose it with itself 3 times, you get back to the identity.
Yeah.
Especially it's also weird and cool because that's like the thing that the geometric series is a formula for.
Yeah.
There's all sorts of cool things about this. Yes. I'm not sure what to say about it though. But
yeah, probably the less the better.
but this one down here is order. It's you know, just translation. This is the one that's infinite. So these numerical labels 2, 3, and infinity
match up with the first Coxeter diagram.
Exactly. That's right. So that's what's going on here.
Mm-hmm.
But John was also hinting that there's another way of drawing this diagram, and again, it is very much more Escher-like, where you well, you cheat a little bit by you can anticipate by knowing that there's big numbers in the diagram, like infinity. You can anticipate that we're going to get something hyperbolic.
Mm-hmm.
So you can draw like a hyperbolic disk, like hyperbolic plane, but drawn on paper as a disk or something like that. So it's, you know, it's this very Escher-like thing where the angels and devils get very crowded as you go to the edges, which, but from their point of view, it's not getting crowded. It's actually, you know, any point is the center of this. And then, right, and then there are some famous conventions for thinking about the hyperbolic plane. Is there a problem here with the whiteboard here? Maybe it's okay.
Yeah, I think it's on my side. I don't know.
Okay, okay. But so right, this is like, what am I trying to say? This is like Lobachevskian geometry or something. And there are some famous models of Lobachevskian geometry. There's one where the straight lines are what? Like that or something like that? The straight lines are straight lines?
Yeah, that's called the Klein model.
Okay. But then there's another one where the, don't tell me. So the other one, and you can like connect any two of these points or something by a straight line. And then I think the one of the other models, do you have a name for that? Was it the Beltrami? No, Beltrami and Klein model.
Poincare disk.
Okay, so let me see if I can remember what that one is. How do okay, I need an eraser to erase the thing. Okay, and this other model, and I'm just trying to make up my mind which model to use. It works either way. But you draw a circle. I think, is that right? All the circles, but it has to be a circle that's orthogonal on the boundary or something like that. So if I want to connect to this point and this point, then I have to make it, you know, like that and that. So orthogonal to the boundary, and then somehow make a circle out of that. So I'm not sure exactly where it goes, but something like that.
Mhm.
And so in one of, yeah, so in the straight line model, things would look like, what am I trying to say? Is there any way to redo here? See, redo doesn't work for me. But okay, so I mean, what am I trying to say? There's one that goes, well, somehow you can right. You can guess somehow that the greens are going to be on the perimeter because they have the infinity label opposite them. So I'm going to have greens on the perimeter. And how does this work? It's going to be, I mean, I'm trying to do John's suggestion of, doing it from scratch, except I'm trying to speed up the from scratch method. So it's not really from scratch, but it would look something like this and this. And sorry. Can I erase that without screwing up the diagram? I'm trying to get the lines to meet there.
Oh, that's pretty good.
Yeah. So is it right that I should have, can anybody help me? Should I have greens right here? And meanwhile, I would have like reds here. And I would have blues.
Rotating around a red.
That looks right.
Order 6, yeah.
Yeah. And blues now have order 4.
Yeah.
Now you keep filling in this diagram, right?
Yes. But so this is the Klein model, but I think many people find the other model more aesthetically pleasing. I think Escher found the other model more aesthetically pleasing. Well, I'm not sure. Maybe Escher experimented with both. But so in the other one, I think some people find it aesthetically pleasing, except that's not an aesthetically pleasing circle because it's not. Let me try to erase. Okay. Black. Try to get it to close up and actually be a circle. Okay. And then it'd be basically the same thing, except with the damn. I'm still just not very good with the erasing and stuff, and I'm doing. All right, let me try to fix it. Circle. And then
Sometime when you want to undo something, tell me to undo it and I'll see if.
Oh, maybe you can undo? I don't know.
Yeah.
And so, I try to put in those other kind of Lobachevskian straight lines.
Mm-hmm.
Have you studied hyperbolic geometry a bit, Chris? This kind of
A little bit.
Picture stuff we're talking.
Yeah, I think I told you a little while ago I was thinking really hard about Fuchsian groups and how they act on the hyperbolic plane.
Yeah, okay, that's good. So this is,
So I've seen a handful of this. I've seen some stuff about SL2Z.
yeah,
Yeah,
yeah.
but
So we're probably this group that we're drawing fundamental domains of, it's probably a Fuchsian group.
yeah.
But maybe like the mother of all Fuchsian groups. It's probably like SL2.
Right, right. So what am I trying to say? So one of the things that's going on here is that don't tell me. Let me get this right. So let me try to quickly redraw the diagram.
You want me to undo something?
I have so many people to blame for why I can't do this. Let's see. Let's see.
Starting with Bill Gates.
Yes, I'm sure they're involved somewhere. Let's see. Green and blue and right. It sort of looks like there's a virtual ink pot over to the left or something, right? That's
Oh,
what
I'm sorry.
the hand is going.
I hadn't even raised this. Yeah, right. Exactly. Yeah.
Okay. And the infinity label is over there. Okay, so it turns out the reflection group here, the thing that's usually called the Coxeter group, but perhaps the Coxeter reflection group, turns out to be PGL 2 comma Z. And but you know, it's acting by reflections half of the time, so it's not acting holomorphically. It's acting a mix of holomorphically and anti-holomorphically. So just the rotation, the Coxeter rotation group that's acting holomorphically, and that turns out by some mysterious coincidence, or maybe it's not mysterious, to be PSL 2Z. And so those things are holomorphic. So we can just give, you know, polynomial or rational expressions for them. So this is the rotations, the Coxeter rotations.
So in general, Chris, the Coxeter rotation group is the group generated by products of pairs of generators.
Right. That makes sense.
For the original Coxeter so-called reflection group. Yeah.
And my guess is that's probably index 2 in the whole thing. Is that right?
Yes, that's right.
Yep.
That's right.
Because all you need is one reflection to be able to get all the others.
Yeah, because if you've got if A and B are generators and you've already got A, B in your subgroup.
Oh, and everything has order 2. Yeah.
So, yep, right. Yeah. Because of everything having order 2. Yeah.
And then is it obvious that PSL2 is index 2 and PGL2? I guess that has something to do with the fact that you have 1 and -1 probably, whereas in PSL you only have 1, something like that.
Yes. So you're talking about over the integers at this point, is that right?
Yeah.
Yeah, you get tricky different answers. I'm getting all these errors here, but maybe I can just ignore them. That's supposed to say index 2, that like you pointed out.
Yeah.
And yeah, so let's see, I can't remember the terminology. What's the Möbius group? Is there a discrete Möbius group or something like that? I mean, the point is, again, this Möbius group, I guess, is like PSL perhaps 2 comma the complex numbers or something like that. And
that's a group of Möbius
PSL.
transformations. Those fractional linear transformations are the
right. And because of the S, I hope I'm saying this right. Is it I was going to say because let's see.
Yeah. Should it not be PSL2R? I don't know why I feel like it should be R and not C.
Well,
yeah.
C,
No, you're right. You're right. There's all sorts of funny things going on here. You're right. You're right.
But
yeah.
maybe
There is an R going. Yeah, right. There are funny games.
It's fun. Yes, so you get to have lots of fun because you can put a P or not. You can put a G or an S, and you can use Z, R, and C. And all three, 2 times 2 times 3 of those groups are important, and you should
Yeah.
study them all.
So
And
part of the point is that the PSL2R is preserving the boundary where the cusps live. Right? Because that's actually the real axis.
Right. Ah,
yeah, so that's relevant for what
So
we're
that's
doing.
actually, that's not just right. So it's like, the PSL2C is giving you some kind of conformal automorphisms of the whole Riemann sphere. Whereas the PSL2R is giving you conformal automorphisms of just the Riemann hemisphere, which is like the Lobachevskian plane.
Yeah.
And it's this PSL2Z, which is I think the most official modular group. That's I was sort of hawing about it earlier. What's the modular group? But that's the modular group. So
okay. Well, okay. There's all these things going on here, and we have these Escher-like pictures, but we also have these other pictures, where
so
where I
15
was trying to
minutes
draw
to
here.
official ending time. I could go on longer, but you haven't racked up any points for your.
Well, what's a good ending time to aim for today? Should it be 4 p.m. or should it be 4:15 or
15 after is certainly fine. Yeah.
all right, okay. I just want to put in some of the red things in
a
here.
modular curve and some numbers underneath it.
Yeah.
Well, okay, but I just wanted to put the red dots in some of these things.
You don't need to draw all that stuff.
Sure you do.
Sure you do. Everyone does.
Well, if you want to draw all of them, you'll be here for a while.
So,
well, you got all this.
Right. I mean, but one of the things that's good to think about is the the nice analytic transformations between these two pictures that we have. The one where the upper half plane versus the interior of the disk. And right, so in the interior of the disk, one of the nice things about that picture is it's kind of democracy between all the cusps. There's nothing particularly making any of the cusps special. Whereas in the upper half plane, it's deliberately been set up so that one of the cusps is very special. It's the cusp at infinity. And that's probably mathematically significant somehow, but I have to think about, how it's mathematically significant. But meanwhile, we really want to apply to this Coxeter group. We want to apply to this infinite hyperbolic planar Coxeter group. We want to apply the philosophy that Chris already mentioned about wrapping up the universal Coxeter tiling. So I'm calling these fundamental domains tiles some of the time. I call this a tiling. And I think probably some of the Escher pictures are referred to as tilings in certain contexts. And but you can take any subgroup and think of that as something to mod out by. And in that way, you wrap up in a branched way, branched at the corners. And you can see it's going to be, the branch points are going to be red or green or blue vertexes. And you get wrapped up non-universal things. And those are going to give us the modular curves. In particular, they're going to be wrapped up enough so that they become finite. Some of these infinite ones could perhaps be considered honorary modular curves. They might even fit somebody's definition of a modular curve, but there's funny things about the infinite ones. It is better or more convenient in some way to require our modular curves to be these finite wrappings up. So in other words, you're modding out by a cofinite,
right?
Modding out by a finite index subgroup.
Right.
So let's start trying to draw some of these. If I can just find my cursor, that will help me draw things. Where did my cursor go? I literally can't find my cursor. Okay.
Versus, well,
Okay, there's my cursor. Okay, now I sort of see it. Okay. And let me try to draw some. So, well, so we already mentioned one. So, right, we're going to be trying to, the first one we drew was the universal one, but we couldn't draw the whole thing because it was infinite. So we just drew a little fragment of it and it suggested to us the whole thing. But when we try to draw actual modular curves, we're going to be sort of working from the other direction, right? We're going to start out with the ones that are as wrapped up as possible and then gradually unwrap them. Every time you unwrap them, you're sort of taking an algebraic extension of your Riemann surface, of your projective algebraic curve. Your Riemann surface is interpreted as a projective algebraic curve. You take an algebraic extension of the field of meromorphic functions on that projective complex algebraic curve. And that's going to give us unwrap things, and it's going to give us these progressive Coxeter unwrappings. So, I mean, I think I did already sort of mention one of these examples that a great example of a finite index subgroup is the group itself. And so that gives us that example that we already mentioned, that looks like the Riemann sphere. Am I doing this right? Riemann sphere. And with the prime meridian on it. And I mean, I don't know. I'm trying to, at the moment, I shouldn't persist in this, but I'm sort of trying to, draw a sort of three-dimensional diagram or something like that of the Riemann sphere. And then I have like maybe green at the North Pole and blue at the equatorial pole, or whatever you call it. And then red at the South Pole.
so why don't you get something even more boring like a point if you take a group and mod out by itself?
Well, it depends on which group that we're talking about. So the Coxeter reflection group is this PGL thing. But a lot of people aren't interested in that because it includes the non-holomorphic part. So for a lot of people, we're just interested in the PSL 2, Z. And we consider that the whole group. And we're just modeling out by that whole thing. So, right, I mean, so for the PSL, for the Coxeter rotation group, the fundamental region includes both an angel and a devil. And that's often called, in certain contexts, that's called a lozenge for some reason. Because I guess because it's like trapezoidal shaped or something like that. Like
I guess it's like
back to back.
A 3D bygone in a way.
3D I mean, this is a very 2D object. I'm not sure what you mean by 3D.
Well, it's instead of two edges that you're gluing together at two vertices, you have two triangles that you're gluing together.
Oh, yes. Okay, yes. Back to back, so it's sort of trapezoidal, symmetric trapezoidal or something like that.
Yeah. But also, John, we're not quotienting by the group acting on itself, right? We're quotienting, I guess you can identify the regions of this with the group, with the torsor argument that you said before, but we're still acting on like the hyperbolic plane, right?
Did I misunderstand John's question? Well, go ahead. Keep going.
So if you were to quotient by the whole group, you wouldn't expect to get a point. You would expect to get a single tile, right?
Right, you're right.
Yeah, so since we're quotienting by an index 2 subgroup, you get two tiles.
Yep.
I mean, there's that SL2R, and if you mod it out by that, you would get a point. But we're modding out by discrete subgroups, so we're getting continuous things, continuous open spaces.
I'm happy.
So if Right, and it, yeah, you know, so this particular Riemann sphere, which by wrapping up as much as possible without doing anything anti-holomorphic, and when I say as much as possible, again, the threshold that we're not allowed to go beyond here is PSL to Z. That one happened to give us the Riemann sphere, which is also called genus 0. But there's no guarantee in general that we'll get genus 0. So, you know, we may need ways to draw higher genus things. So I'm not sure how good flat paper is for drawing higher genus things. But certainly for the genus 0 ones, we can, right, one of the ways to draw genus 0 things on flat paper is to just sort of adopt the point at infinity philosophy, you know, either don't draw the point at infinity, or sometimes I draw the point at infinity as like a perimeter, so I can fit the whole thing into a finite canvas or something like that. And again, just having cursor problems here. Okay, sorry. So let me try to redraw this example in a point at infinity style. So what would it look like? It would look like something like, perhaps I'll like put a green point at infinity, and then there's a blue point and a red. Is that blue? Yeah, I think that's right. And a red point somewhere in the middle. And maybe it looks like this. So topologically, that's the completely wrapped up thing.
Yeah, if we collapse that whole green circle
To a
to a
point.
point, it becomes the picture we had before.
So right, that's our first example. It's very degenerate, but let's do the split screen thing anyway. Okay, let me try to draw a little split screen thing here. So let me try this. Sorry, screwing up here. Okay, so the splitting of the screen for me is like somewhere here. And over on one side, I have boy, now I really have trouble deciding whether the moduli stack should go on the left or should the moduli stack go on the right. I guess I'll put the moduli stack on the left, I guess.
Good.
And that's the wrong color already. So let me try to erase that. And
I'm trying to imagine what this is the moduli stack of, so that I can find the things, examples of these things that it's of. So,
all right, so there's the blue.
So they are elements of PSL2 R mod PSL2Z.
Say it again. I didn't quite follow. Can you say it again?
That's a good way to think about it.
I'm trying to think of what the points in this moduli space are. And so for starters, they are elements of PSL2, PGL2R mod PSL2Z.
Well, can I start drawing some examples?
Well, I was just trying to figure out what they're examples of, but okay.
Well, I think you'll get the idea, though.
Okay.
So, you know, let me draw my little. That's my little "you are here" arrow.
Right at the blue dot.
Right at the blue dot. That's right.
Okay.
And
where I've lived my entire life.
So this one looks like this. That's supposed to be a perfect square. It just, you know, it's just an elliptic curve that I get by wrapping it up like that.
So why do I get an,
Yeah, I'm also confused.
how is that point? You're not gonna tell me what these points are in general?
Yeah, we will. So, okay, so let's think about how this works.
Okay,
So there are two very important ingredients in an elliptic curve, in a complex elliptic curve. Two very important ingredients. So much so that you can sort of think of the concept of an elliptic curve, the concept of a complex elliptic curve. You can think of it as just kind of a marriage of these two ingredients. And the two ingredients are a complex structure and a lattice. But these two ingredients, they need a common ambient context in which to live. So I guess the common ambient context in which or on which they live is they live on a real vector space.
Yeah.
two-dimensional.
A real two-dimensional vector space. Yes, a two-dimensional real vector space. And so one extra ingredient, one extra structure that you can add is a complex structure. The other extra structure that you can add is a lattice.
Which I guess amounts to a choice of basis, right?
No. it's-
That's more structure, right? A lattice has many different bases in general. And those
True.
you know, SL2Z acts on those bases.
Yeah, you're right. You're right.
I mean, so does GL2Z. There are some confusing things here, but it sounds like what's going on here. It sounds like what's going on here is that we have an ambient group. And yeah, so there are many different variations of how to do this. I'm not sure I'll get the best way to do it, but it should probably be good enough. So it sounds like the ambient group that we want is probably something like the automorphism group of our ambient context. So so that's a real two-dimensional vector space. So that sounds like the automorphism group of that would be sorry. What's going on here? It'd be GL2R. That is the automorphism group of our two-dimensional real vector space. And then there are two subgroups that correspond, you know, that preserve these two extra structures. So one of them is discrete and one of them is continuous. So you can have GL2Z. That preserves a lattice. Again, I'm tempted to make it SL2Z instead of GL2Z, but I can't quite think of a justification for that. There's probably some justification for it that we could come up with, but at the moment, it seems like I'm saying that we should use GL2 comma Z, the automorphism group of a lattice. Right? There is some sense that, yeah, that's, if you preserve a lattice, then it's GL2Z. And if you preserve a complex structure, then it's GL1C. And these are both subgroups of the
Yeah. And the second one will preserve the orientation for sure. GL1C.
Yes. So I mean, so there's a general thing that you can do when you have a span like this, right? This is a span of groups. Is it a span or a cospan? It's a span. No, it's
cospan.
No, this is the cospan.
Okay. Boy, is that confusing me? Does it make sense that this is a cospan?
It's always
respect,
annoyed
okay.
me that co-spans are associated to pullbacks, which are a limit. It feels like a co-span should be associated to a co-limit, but
Yeah, no, I think what's actually going on
unfortunately,
here is
life is bad.
there is this is a cospan, but it's much better to think of this as really a span by thinking of the associated homogeneous spaces to the subgroups.
Ah,
So it's something like again, there are many variants on how to do this, and I could easily fail to do the optimal way. Just trying to maybe I should try to draw the homogeneous spaces or something like that. So there's like there's the homogeneous space of wait a minute. Sorry.
well,
Let me try to fix this. First of all, since we're doing something very abstract and very generalizable here, so let me try to get away with just using like let's see, I'll use sorry, what's going on here? Okay, I'll use A for ambient group, and then I'll use
what? D for discrete and C for continuous or something?
I was just gonna use H and J or H and K. But you're very much right that there is a pattern that becomes, for mystical, mysterious reasons, there's a pattern where H is one of H and K is discrete and the other one is continuous. Well, it gets more than that. The patterns are more striking than that. It's like one of them is discrete and the other one is co-compact or something like that. I forget. But there's all sorts of interesting things, pattern shape. But for this abstract pattern, all we need is two subgroups. So A is an ambient group. H and K are just subgroups. And then you get these homogeneous spaces. So these are not like group homomorphisms. They're just maps from what is it? A mod H and A mod K. And then at that point, you've got a span.
Mm-hmm.
And you can think of that as a span of groupoids, actually. And
Sure.
but what it really is morally is it's like what am I trying to say? There's so many different ways of thinking about this. I guess one way to think about it is, let's see, if you have a span, see now, okay. Let me think what you're saying. See, maybe I should have done what Chris said. Maybe I should have stuck with the cospan. But think of it as a yes, okay. Right. So we have a okay. So Chris suggested something about taking a pullback of a cospan, I guess. Is that right? So the pullback of a cospan is a span. Now, if you took that pullback in the category of groups, then you would get just the intersection of H and K. But it's somewhat more interesting, but closely related, to take the pullback in the two category of groupoids.
Okay.
So,
and I guess now you want some sort of two pullback as well.
Two pullback, that's right. Yeah. That's right. which I would probably just call pullback if I'm dealing with groupoids, but
That's
I don't
reasonable.
know, I don't know if that's the best notation, terminology.
I'm just making sure that I understand what you're saying.
Sure, sure. And it really is crude, but yeah, you should have some sort of terminology for distinguishing between the two, because they're very closely related, but but there's a very important difference between them. So right, the intersection of two subgroups is another subgroup. So it's still a group, but the two pullback here is not a group, it's a groupoid, because it sort of corresponds to all the different ways that the structures could correspond to each other. So this is also, this is also sometimes called the double coset story.
Oh, interesting.
This is, but so the moral interpretation of double cosets is that they give you geometric orientations between geometric structures. And so one of the things we're saying is that roughly, to a first approximation, you can think of the moduli stack of elliptic curves as being the double coset space for that pair of subgroups that we mentioned, the lattice preserver versus the complex structure preserver, because it's all the ways that there are beautiful, nice stories about this. There are many different ways of thinking about it. You can think in terms of double cosets. You can think in terms of pullback of groupoids. You can think in terms of Hecke operators and Mackey's intertwiner theorem. There's beautiful stories about this, but let's not try to go too far into that right now. Let's just try to use the intuitive idea that you can consider all the ways in which the space of all ways in which two structures can be oriented to each other. And that's, so sometimes I'll call that an orientation space, or it's like.
This is orientation in a very, not like.
Yeah.
Not in the differential, not in the plus or minus kind of sense.
This is orientation in the
ways that they can be related to each other.
Yeah.
So this is, let me say it another way here, like we'd be getting the groupoid.
How do you orient yourself to that piece of
right.
furniture over there? You could
Right.
be.
Yeah. Like orientation week at the beginning of any college, right?
Yeah.
they try to orient you in the college. So.
Well, they have one favored orientation, but the students have a different idea. They have a different orientation that they want.
Sure. Yeah. Well, they but they start out with no orientation. But anyway, so what we'd get here if we did this weak pullback in the specific example, I'm just going to blatantly say it, is that we would get like the groupoid of two-dimensional real vector spaces with a lattice in it and with a complex structure on it. But and it's a groupoid. Talk about isomorphisms between such things, but there are many different isomorphism classes of such things, because there are many ways that there are not many isomorphism classes of lattice. They're all isomorphic to each other. There are not many isomorphism classes of complex structure on a two-dimensional real vector space. They're all isomorphic to each other. When you put down both, then there's many different isomorphism classes, because there could be like a square lattice, and that makes sense once you have a complex structure. Complex structure lets you know what angles are, because you can multiply by e to the I theta. So there'd be like the square lattice, and that would be non-isomorphic to some other parallelogram-y lattice.
Yeah.
But
they also have isomorphism. So you're really getting a groupoid thing, which is a stack.
And it's also it's completely believable that this should have something to do with the moduli stack we've been talking about, because
in an informal sense, it is the moduli.
The lattice with a complex structure, and that's
so it's starting now.
It feels like we're heading towards elliptic curves now.
Yes. Yeah. But notice there's all sorts of glitches and things here. One of the big glitches here is, again, that at the cusps we don't know what to do. So again, with my split screen drawing, at the blue point I draw a square parallelogram. At the red point I draw the equilateral triangle, the parallelogram that you get from that. That's the elliptic curve. And But what do I draw at the green points, at the cusps? I don't know what to draw there. It's like, you know, the split screen malfunctions as, you know, that. And there may very well be some good thing to draw at there, but I don't know what the good thing to draw is at those green cusp points. So those green cusp points are very mysterious to me. I don't know what the picture should be, what the split screen should, what the other half of the split screen should display when on the left side of the screen we are at a cusp. So maybe we have time for one more example before we quit. So
I want wait.
Go ahead.
I didn't fully see like a systematic working out of how you got from the stuff you were doing before you drew that
Yes.
span or that pullback, weak pullback that we were talking about. Sorry, I didn't fully see a connection between those stuff near the bottom of the picture and the stuff on the top. So on the top, we started out drawing this Coxeter tiling, this universal one, and then this
anti-universal one, the one that's, you know,
well, yeah, first the universal one, and then this anti-universal one, this other one.
initial versus terminal. Yeah, go ahead.
But the way I'd been thinking of what we were doing is that the upper half. Maybe I'll get it. So what was the upper half plane? Was that like GL1C over mod GL2R already? The upper half plane was already a homogeneous space of something.
That's right. It was a single coset space.
And it was basically, was it GL1C over GL2R? Or maybe that was like the upper and lower.
That was it was SL. It's supposed to be something like GL2R modulo GL1C.
Oh, I said it completely backwards, but yeah, I said it all wrong. But okay, good.
But I'm not sure. I'm not sure I said it exactly correct, but it's very close. You know, it's the
GL2R has 4 real dimensions. GL1C has 1 complex dimension or 2 real dimensions. So 4 minus 2 is 2. So it'll be something with 2 real dimensions. So that's
it should be something very much like the upper half plane, or maybe I don't know, maybe it's 2 copies or whatever.
Okay. So I see. So you were what you were doing, I'm trying to foist more order on it than naturally emerge. But anyway, so what we did is we started out with GL2R mod GL1C. That was, let's hope it was like the upper half plane. And then we then we modded it out by GL2Z. Is that what we did? And then we got this. When we modded it out by all of GL2Z, we get this little.
I mean, again, there's so many ways of thinking about this. It's hard for me to get it straight under pressure, but probably what you're saying is correct. Go ahead, yeah?
Yeah, well, I guess I'm just trying to get it. I can't slide back up. You got like a lock on it or something.
Where do you want to go to?
I just wanted to. Anyway, I was just wanting to look at go up above what is now. Oh, you can't. You see a different thing than I do, so there's no point. For some reason, I'm no longer able to. Oh, I just did something. Anyway, this like this Riemann sphere with these 2 hemispheres.
Yes.
So like that.
That's the same as the picture on the left side of the split screen.
Right. But it came, I'm just saying that I think it came by, we got it by taking a quotient of the complex upper half plane, or the whole complex plane by something. So I'm thinking we got it by taking GL2R mod GL1C or something like that, and then modding that out by GL2Z. But I don't know if that's exactly right. But I was wanting to like have some story starting from the stuff above the page and then leading to this little span you drew.
Yeah, there certainly are things like that, but I'm I'm just not good at doing this under pressure when we're trying to wrap things up here.
Okay, fine.
Um,
Anyway, it's something like that. And then, but then we also see that once
I
you
was
get,
hoping I was hoping if we did an example that it might answer your question.
okay, well,
Or-
okay.
And you know, we barely even have time for an example, but let's
Okay, go.
try to do one quick example here. And again, I'm not even sure what I'm doing an example of, but after I do the example, you may explain to me what I'm doing an example of.
I know, that's how it works. Yeah, that's right.
Okay. Right, that is how it works. So what am I trying to say here? That right now I'm scrolling down on my own screen where nobody else can see. Okay.
I can do
And-
that.
Also, it seems like some of the problems here are because we've drawn too much. So maybe I shouldn't have
right.
looked at last week's drawings. So I'll fix that for next week.
Well, I'm not sure about that. We'll have to worry about that later, but not right
Yeah,
now.
I can worry about the technical aspects of this, but
Okay. But what am I trying to say? So right, maybe I should draw my picture, actually draw my example.
Yeah, and then I'll figure out what it's an example of. That's my job.
Right. So I'm
about
gonna give
here looking pretty.
I'm gonna give a subgroup of our discrete group. I'm gonna give a subgroup of our Coxeter group.
Okay.
Um,
You
and
gave away what it is.
what?
Never mind.
I don't
I
understand.
thought teachers are supposed to give examples, but not say what they're examples of, and the students have to guess what it's an example of.
Well, no, but I'm gonna give example of something, but it's really secretly an example of something else, and that's what you have to be. So we're gonna have this thing called gamma sub 0.
I do like that you wrote out the word gamma.
I just hate different fonts and different alphabets and things like that. So gamma sub 0. Well, okay. So there's a whole sequence of subgroups here, and which way do they go? Do they get bigger? So there's like, maybe I should start with 1, and then let me think. Is that a really? I have to stop and think about whether that's a really big group or a really small group. Don't tell me the answer yet. Let me think. Let me see. I think that's a really big group. That might be equal to SL2, let me put a question mark there, to Z. But just by definition. And then it's got these subgroups. Gamma 0 sub 2. And so forth. Well, but what I mean by so forth, in this case, by so forth, I mean gamma 0 of 4. Because to get the comparison maps, I need the divisibility here. So if I just keep on taking powers of 2, I'll get the
Have you told us what gamma
Yeah.
0 of n is supposed to be yet?
I could
No,
tell you, but no. That would make it too easy.
That would make it too easy. Okay.
So what it is gamma 0 of n. It's the subgroup consisting of the. Boy, that came out strange. That doing it right? It's little 2x2 matrices. So things that are in SL2Z to begin with, but that have
if you want divisibility, okay, I think I see where we're going with this.
So I think it's going to be something like C is equal to 0 modulo n.
Yeah.
I think that's the definition of gamma sub 0 of n.
And that makes
There's
sense.
lots of different tricks that you could do, but these are like, I guess you could say they're upper triangular mod n.
Yeah. Yeah.
They also consider lots of others. That the 0 means like which game we're playing, I think.
Yeah.
Yes.
Oh, when you say the zero, you mean the subscript gamma sub zero?
Yes, I think that's what John
The
means.
little zero subscript there.
Yeah.
Yes.
The
yes.
little zero subscript doesn't mean anything mathematical. It means that we're playing the zeroth game.
Zeroth game that they thought of. I mean,
Yeah.
yeah, there's another one that they defined called gamma. There's another one defined called gamma sub 1. But it's not a very systematic naming system.
Yeah.
Right, okay. So it is worth pointing out in the notation that, the thing inside the parentheses is a very systematic input or parameter or something, but the subscript 0 is just, a convention of some kind. And did I really get it? You think I got it correct that it sounds like you're saying that the constraints are getting more severe.
Yeah, that's
n is
right.
getting
It's
more
harder to be
divisible.
a multiple of 4 than to be a multiple of 2.
Okay, so hopefully hopefully I did get that part of it correct.
Yeah.
And so these subgroups are things that you can, mod out the universal thing by. So, so let me see if I can remember the index of some of these inclusion homomorphisms. I think this is index 3 here, I think. And I think all the rest are index 2. So the composite index is, 3, and then 6, and then 12, and then 24, and 48, and 96, et cetera, et cetera. And so those indexes, if you think about them, that's telling you the number of fundamental regions in this orbit space that we're getting. So, this one, right. So, okay. So an accompanying notation here is there's something called x sub 0 of 1. And there's something called x sub 0 of 2. And there's x sub 0 of 4 and x sub 0 of 8. And, now the arrows are going the other way. Am I seeing that right?
And are these like the associated homogeneous spaces or something?
Yes, but I'm still not sure I got the direction right here. Let's see. So the arrows, what?
Yeah, you're modding out by smaller and smaller subgroups, so you get
the arrows could be going the same way instead of different way, right?
Sorry. What?
I mean, because it's like progressive unwrappings.
Yeah, you're right. It's funny how it's pointing the same way. Yeah, okay.
There's probably some very sensible reason for it.
Sure.
So but right, but these are like
you're right.
surjections now. These are
I just expected it would
unwrappings
be
or something.
Yeah.
That was stupid. Okay.
Yeah, I was expecting it to be the other way, but it's apparently this way.
I guess that makes sense. Z mod 4 surjects onto Z mod 2, right?
Say that again?
Z mod 4Z is a subset of 2Z.
Yes.
So good. And Z mod 4 surjects onto Z mod 2.
Yes. Yes. I mean, it's right. And there is just something like,
we've done the exact same
covariant operation of, there's
this
covariant functorial operation of cokernel or something like that.
Yeah.
So that's perfectly covariant, and it turns injections into surjections or something like that. So there's very simple things going on here, which I nevertheless managed to get myself confused about, but I try not to think about the confusing parts too much. Or I try to think about the unconfusing parts instead of the confusing parts. Right, so these are progressive unwrapping. So right, we already drew the x sub 0. The x sub 0, that's that terminal thing. It just had one fundamental region. So the next one has 3 fundamental. The first one just has 1 tile, and it's all wrapped up by itself. And that's the
one pair of tiles, you mean?
Yeah, one tile.
Yes. I mean, sometimes I call the tiles, the things that are 2 triangles stuck together. Sometimes I call the tiles things that are just one tile stuck together or something like that.
Okay, fine.
So,
Yep.
you know, it's, if you're talking about the rotation group or the
Yep.
reflection
Okay.
group.
Fine.
So, so, you know, this next thing has these 3 bitiles, and then the next thing has 6 bitiles, and then the
Yeah.
next thing has 12 bitiles. So let's try to draw the one with the 3 bitiles. And maybe I can cheat by looking in one of my paper notebooks here. Well, we are getting very close to maybe I should just draw this one and then maybe try to draw a little bit of a split screen and then, you know, declare victory. And then we'll really try to do real examples next time. Let's see, do I have the pictures here? Okay, I think I've got a picture here. Let me see if I can draw this. So this is supposed to be x sub 0 of 2, if I didn't screw it up. So let me just try and draw it. All right. Let's see. What color is this? I'm having trouble reading my colors in my notebook. I think there's a green there and a green there. I think there's 2 greens. And then I think there's 2 blues. Like there and there. And there's 2 reds. Right. So, right. For today, this is going to seem mysterious, but when we explain it next time, it's going to hopefully become very unmysterious. But we're at least going to draw the picture right now.
I mean, at the very least, it's looking like it's going to be a double cover, which is
Well,
good.
I think it's actually a triple cover. Am I confused? Let me see. I think this is going to be because you know it's going to have right. The generic points are going to have 3 copies.
Ah, right, but it's ramified at the vertices.
It's ramified at the yeah. So apparently, maybe it's ramified at all 3 colors. I'm not quite sure. So I think it's going to be like this. And
so before we had 2 triangles, which were weird triangles.
Say that again.
Before the previous picture had 2 triangles in it.
Now we have 6.
And now this one has 6.
Now we've got 6. So
which certainly does feel like a triple cover.
So that's good.
Yes. Now, so okay. So these 3 tiles or 3 bitiles, it turns out, for reasons we'll have to explain next time, that good names for these 3 tiles are infinity, 0, and 1.
Mm-hmm.
And I guess it's related to the idea that infinity, 0, and 1 are the 3 points of the projective line over the 2-element field.
Ooh, okay.
So I'm gonna in the picture somewhere, I'm gonna put these labels infinity, 0, and 1. And it might not look like I'm putting them in a sensible place, but I actually think I am putting them in a sensible place. So I think it's gonna be an infinity there, and there's an infinity there, because there's
labeling the faces or the edges.
They're on the edges, but remember,
but it's labeling a
bi-tile is 2, you know, tiles reflected across an edge. So that's the center edge. So the fact that these are both labeled infinity means that they are actually glued together.
Right.
And I think, right. So I'm actually putting the labels on the edges that connect red to green for some reason. You know, that's just a convention that happens to work good in this case. So this one is 0, I think. And this one is 1. And right, it looks like infinity is occurring twice, but it's actually only occurring once.
That's weird.
And I think that, you know, you have to identify, you know, like you identify this infinity with this infinity. I think you also do the same thing up here. I think if this, you know, if this is like A, I think this is also A over here.
Mm-hmm.
And,
so is this another Riemann sphere as a surface, I guess?
Yes, it is. It is. Actually, I'm a little bit confused. how can that happen? That see, somehow I was expecting, I know how to get genus 0, double covering genus 0 with 2 branch points.
You
where
kind
you
of
just
triple
have-
cover with 2 branch points if they have order 3.
Right. But this looks like something different. This looks like it has 3 branch points and they're ordered 2 or something like that.
Oh,
Or
the
something.
branch points are all the different colored dots.
I think so. And do they all look?
Are both those blue dots the same dot? Those are different dots, right? Those are different.
The 2. Oh, okay. Oh, okay. So you're telling me there is only 1 red dot in the picture. That's what I missed. Is that right? There's only 1 red dot in the picture.
It looks like there's only 1 red dot. I think that's right.
Yeah, but there are generally 2 blue dots and generally 2 green dots.
So it's some funky branch triple cover of the Riemann sphere with
I think it is, but it confuses.
2
confuses
blue
me.
branch points, 2 green branch points, and 1 red branch point.
Yeah, it's going to be much easier to understand this, when you have more time to do. Right now, we're just sort of, gawking at the picture, and desperately trying to wrap up here so we can go home. But is there anything more to say here before we declare victory? Let's see. So yeah, we're going to try to convince ourselves that this is a threefold branch cover, and we'll try to figure out exactly where the branch points are, and we'll try to use, what's the name for that formula that you use for calculating the genus?
Riemann-Hurwitz
formula. Yeah, Hurwitz formula. So we probably should, maybe only for homework, but we should probably at some point invoke the Riemann-Hurwitz. We may have modified versions of the Riemann-Hurwitz formula that are more combinatorial in flavor, but that serve the same purpose to help us calculate the genus and check that we've got the correct genus and stuff, things like here. So, okay, let's just try to do a little bit of split screen here. So like, let me see if I can tell you like what this blue thing looks like versus this blue thing. So I'm not going to tell which is which, but I think one of them is going to be like a square. So well, remember, for me, these elliptic curves actually have base points. So, for me, the base point is the 4 corners. Those are all the same point of this rolled up square. And then because the n we chose is n equal to 2, what we're thinking about here is 2 torsion points on this elliptic curve. And it turns out that there are 2 different kinds of 2 torsion points on this is a Gaussian elliptic curve, right? A square, I call a square elliptic curve. I call that a Gaussian elliptic curve because it's related to the Gaussian integers and stuff like that. And because Gauss actually, probably worked on that or something. But so you could put a 2 torsion point right there, but you could also instead put it right there. But those aren't really different in terms of the marked elliptic curve that you get, right? So what we're giving away here allegedly is that this moduli stack is going to be the moduli stack of elliptic curves with a certain extra structure, and the extra structure is a choice of 2 torsion points. And so let's say a choice of non-trivial 2 torsion points. So you can't just use the identity element. So there's all 4 2 torsion points are right there. But the 3 non-trivial ones are the ones that are not the identity. So there are 3 to choose from, but that's not giving you 3 different isomorphism classes. Because if you put the
2 on the edges are the same.
If you put it on the horizontal edge, it's just like putting on the vertical edge. But if you put it in the middle, that's genuinely a different isomorphism class of marked elliptic curve.
Cool.
Right. And that's why it's ramified in this way, because if you have something less symmetric than a square, then you can distinguish between the two edges. Is that right?
I think that's right, but again, I feel like I'm under pressure, and I'm not sure I can give really good answer. Like, one of the things that's confusing me is I can see that there are 3 points to choose from. Right, generically, all three.
Exactly.
Right. Oh, okay. Maybe I do understand what you said. Yes. So if this were a random parallelogram, then you would be able to tell the difference between all three
Two edges. Exactly.
points. But
But
a
because this is
Gaussian
a
thing has a
symmetric-
special symmetry which prevents you from being able to tell the difference from horizontal and vertical.
Yeah.
And that makes the Gaussian point a ramified point in the moduli stack or something like that. Yes.
And so then what should the red point be? The red point should be a parallelogram where we can't distinguish the edges or the center, right?
That's a good question. It sounds like the picture is predicting, there's only one red dot, so it sounds like
Exactly.
It sounds
So
like it's predicting that they'll all be the same. But let's try to draw that and see if we really believe that. So what does that look like?
And then I
So
might
it's
have
like,
to head out.
those are equilateral triangles. That's supposed to be equilateral
We're
triangles.
supposed to know that the red one has a lot to do with the number 3 and with the elliptic
Yes.
curve, where
Yeah.
you draw a bunch of equilateral triangles in the plane and you build a parallel.
Ah,
So maybe you're telling me that this one is even more ramified, right? Because the generic points occur in 3 copies.
exactly.
Right.
And you
Okay.
can see it now as well because the edges are the same length. Those 2 points are the same. But also
Yeah, that third
think about,
edge, that
you
that
could think about
edge, the
chopping this
diagonal
parallelogram
edge that
in
Jim
half.
isn't actually drawing. Yeah, it's just like the other edges. Yeah, that's cool.
That's really cool.
Thanks, Chris. That's great. I didn't figure that out at all, but yeah, now it's all coming together.
So yes, all of these modular curves, this is our punchline for quitting. All of these modular curves are going to be the moduli stack of moduli stack of elliptic curves with some extra structure. And the extra structure is generally going to have something to do with like these torsion points stuff.
Right.
We're already seeing that in this one example that we've done of x sub 0 of the number 2. And we're going to do plenty more examples. And one of the things we didn't even do yet is we didn't even try to write these number sequences that represent the dimensions of spaces of modular forms or something like that. But we're going to try to do that too.
Yeah.
So even though we're creeping very slowly here, I still feel like we're making progress. Anything we should do before we quit, or are we pretty much done now?
I think I need to run.
Okay.
Yeah, I should go too. Yeah,
Okay,
I
me
should
too.
have gone.
Actually, not me. I'm not in a hurry, but nevertheless. Okay. So
Well,
I'm just gonna
Yeah.
lounge around
two
here.
people run away, then the third person is relative to the center of mass also.
I do have to run later today, but much
Yeah,
later.
yeah. No, we should quit now. And we did.
Okay, so thanks a lot. This was great. Even if we're going very slowly, I still feel like it's good progress.
Yeah,
Yep.
these examples were very helpful. So
Okay.
Great.
Thanks a lot.
all right, perfect. Take care.
Okay.
all.
Yep.
Bye. How do I turn this up? I'll figure it out.